Okay, so here's where we were. In the last class, we discussed about Fermi level, and we learned how to calculate the number of electrons in the conduction band and number of holes in the valence band based on uh, the Fermi function as well as the density of state function in the conduction band and valence band. We also discussed the concept of the probability of finding a hole, which is basically the opposite of Fermi function. And we calculated some numbers, number of electrons in the conduction band and number of holes in the valence band. And we noticed the symmetry between these two equations. And that's something that will keep coming back over and over again as you study semiconductors, more or less. There will be two kinds of semiconductors, dope semiconductors, that we typically use. We will be typically using N-type semiconductor and P-type semiconductor. And turns out whatever you do for N-type will often be symmetric or somewhat similar for the P-type. So that simplifies our job. So even if you don't pay attention primarily to one kind and just focus on the electron part, you could ideally, for the most cases, just portray that in terms of whole and get similar equations out of it. And you keep seeing that over and over again. Now, let me just quickly point out the similarity between these two equations. Both had Fermi level showing up inside the exponent, and both had temperature as a variable. And for the number of electron, we were dealing with conduction band. For the number of holes, we were dealing with, valence band here, as you see. And as an extra constant for the number of electron, we had NC, which is basically a constant with additional constants inside it, right? We had temperature, Planck's constant, effective mass of electron, all put together in one package inside NC. So we need to give NC a name, by the way, because we'll keep using it over and over again. We might as well give it a name. So we decided to call it effective density of state function in the conduction band. So it's a mouthful, but it is essentially like a constant, like a modifier in front of the exponent. That's all. Okay, just keep that in mind. It's not as difficult as it sounds in terms of the name, but we still have to keep that in mind, because in math problems or in other textbooks, they will keep referring it as effective density of states in the conduction band. Okay, so same thing applies to NV, which will be effective density of state function in the valence band. And it had similar structure as NC, except for one aspect. Instead of effective mass of electron, we had effective mass of holes. All right, so now let's get to the next slide, and let's do a math problem here together. Typically, I have these simple math problems as examples, because that helps solidify the usage of these equations rather than the origin of these equations. I think at least understanding the origin is necessary for us, because we shouldn't probably keep ourselves in the dark entirely about the origin of these concepts. But in the end, what matters is, can you use them as an engineer? Okay? So that's what these examples will illustrate. So let's see what the question asks. Calculate the thermal equilibrium hole concentration. So P0, and I think I mentioned that 0 represents thermal equilibrium, and P represents hole, N represents electron. So we have to calculate P0 in silicon. So all of these are important clue, by the way. At 400 Kelvin temperature, assume the Fermi energy is some electron volt. Some electron volt above the valence energy. We'll, calculate all of them soon. And they have given us the value of NV for silicon as this. Okay, so all of this information are given. So let's start with the equation that we need to use to calculate the thermal equilibrium hole concentration. We need this equation. So let's start with Fermi level energy. Let's see whether they have given us the Fermi energy. So the Fermi energy is 0.27 electron volt above the valence band energy. So can I write it this way? Fermi energy is valence band energy plus 0.27. As simple as that. So if you replace that here, these EVs will cancel each other out, and you only have a number left. Simple. In terms of KT, K is Boltzmann constant. You could just get it from your calculator or Google. And T is temperature, which is 400 Kelvin. So you just plug it in and you get some numbers out there. Finally, you see the only thing that we need to plug in now is NV, which is also given But there is a small catch. Notice that. So the catch is they have given us the value of NV at 300 Kelvin temperature. But we have to calculate the whole concentration at 400 Kelvin temperature. You might wonder, what's the big deal? We could just, this should be a constant. But remember, NV is not really a constant. It's like, it looks like a constant, it looks like a modifier, but it's a function of temperature. Notice that NC and NV, they're both functions of temperature. There is temperature sitting in here, right there. So just to illustrate the significance of that, that it's not just any other constant. It's a parameter that is a function of temperature. So we have to basically calculate the NV for 400 Kelvin, which is the target temperature for our case. And the way we could do that is just look at this equation. Let's consider that for temperature T1, you have NV1. And then for temperature T2, you have NV2. Let me just do it here. MP star KT2 H square 3/2. So now, if you, maybe this is equation 1, this is equation 2. If you divide equation 1 with equation 2, you get NV1 over NV2 equals T1 over T2 power 3/2. Simple, all right? And now, just plug in T1 as 300 Kelvin and NV1 as whatever you get at 300 Kelvin, okay? So you plug in this value here and temperature T1 as T1. And the temperature that you need to work with is 400 Kelvin. So T2 would be 400 Kelvin. And then you can calculate NV2. NV2, simple. And all of this have been, simplified here in this simple math expression. It doesn't show you the steps, but this is how you get the steps, by the way. So after you calculate NV, you plug it in and you get P0. Don't worry, you'll have some experience and practice run in your homework. So I don't want to spend too much time here. And hopefully you'll be more comfortable using these equations moving forward. Now let's get to the next concept, concept of intrinsic carrier concentration. Now, notice one thing. When a semiconductor is intrinsic, and first of all, I haven't even talked about what intrinsic semiconductor is. An intrinsic semiconductor is another name for pure semiconductor. So imagine you have conduction band, you have valence band. So apparently, when an electron goes from valence band to conduction band, you create number of electrons in the conduction band, and you can calculate that. At the same time, simultaneously, when an electron leaves from valence band to conduction band, it creates a hole in the valence band. Basically, the hole is nothing but absence of electron, right? So it creates an equal number of holes, by the way. This is important. Keep this in mind. Equal number of holes, because the origin of the electron is nowhere else but the valence band itself. So when an electron goes from valence to conduction band, it basically creates an electron hole pair. So it's basically a kind of like a positive hole and a negative electron. So they are always created in pairs in case of an intrinsic semiconductor. Something that's pure, right? No doping or anything. So now for intrinsic semiconductor, can I say that number of electron and number of hole will always be the same because they are created in pairs all the time for intrinsic? And that argument will be used here. So if N0 is always equals P0 for intrinsic, we might as well intrinsic. We might as well represent that with something else. So let's do that. Let's use Ni. I stands for intrinsic. And N is basically just a number. So it shows the number of carriers. Instead of electrons and holes, we could just say number of carriers. So this is the old equation that we saw before. All I'm going to do is represent N0 as N1. That's all. Similarly, this is also the old equation that we noticed before, P0. All I'm going to do is represent this as N1 as well. You might have asked me, why not P1? Well, we are trying to kind of make them exactly the same. So we have to agree on one notation. So people agree to use Ni, which is intrinsic carrier concentration. Okay. So now forget about the rest. Sorry, I meant to keep this. Forget about N0 and P0. We are going to use Ni for both electrons and holes. Okay, so these two equations are valid for intrinsic semiconductor. Now, let's consider this is equation 1 and this is equation 2. One deals with conduction band, the other one deals with valence band. But for both cases, the number of carriers are the same. And by carrier, I mean for conduction band, you have electrons. For valence band, you have holes, but they are both carriers. That's why I'm just going to use the word carrier from now on. So if you multiply equation 1 with equation 2, let's see what you get. On the left-hand side, you get Ni times Ni, which is Ni squared. On the right-hand side, you get Nc times Nv, which is here. And then just to remind you, if you multiply exponent for x and y together, you basically just add up the two, powers. That's all. So basically, you take this exponent, multiply it with the other exponent, and then make it one exponent. And all of these things will be basically just added up. Okay. And this intrinsic Fermi levels will cancel each other. You have EC minus EV. And what is EC minus EV, if I may ask? Remember, this is your conduction band, this is your valence band, and this is the energy scale. It's as if a Y scale, by the way. So as you go up, you're looking at the Y scale. And if I ask you what is EC minus EV, that would be this quantity, and this quantity had a name. If you remember properly, that was the band gap. Okay, band gap. So I'm gonna replace EC minus EV as band gap EG. So this equation, this seemingly simple equation, Ni squared, Nc Nv exponential minus Eg over Kt, is a very important and widely used equation in semiconductors. It correlates the band gap with the carrier concentration. Yes, it is intrinsic carrier concentration, but something that has intrinsically more carrier is typically a better conductor. Remember that, or it is easier to make it into a better conductor. So it shows you that there is a relationship between the band gap and the carrier concentration that you can get out of the band gap. The higher the band gap is, just notice this from here. The simple math equation, Ni squared. I mean, I wish I could ask and take your responses, but I'm going to ask the question anyways and respond myself. So if you have a higher band gap, okay, e.g., notice there is a negative sign in front of band gap. So the higher this quantity is, the lower will be this overall exponent value, and eventually you'll have a lower Ni. So higher Eg will lead to lower Ni, which represents if the band gap is higher, this material will no longer really be a semiconductor. It will be essentially an insulator. And there is another way to look at it. Let me just explain that here. Oh, let me do that here. So imagine this is EC and EV, and let's consider another case where you have EC here and EV here. So the difference between the two is in band gap. So here you have EG1 and here you have EG2. Apparently EG2 is far greater than EG1, which represents, as I just told you, Ni squared would be related to exponent minus Eg over Kt. So apparently the higher the Eg is, the lower will be the intrinsic carrier concentration. So doesn't that make sense? Let's see whether it makes sense intuitively. Imagine you have electrons here, the valence bands. For lower band gap, it will be possible for the electrons to get some energy, maybe thermal energy, and jump up to the conduction band and create electron hole pairs. So now there is the electron hole pair over here. But for such a huge band gap, even if you provide some external energy, the electrons will probably not be so easily able to go to conduction band and create electron hole pair. So that's why the intrinsic carrier concentration will definitely reduce. Only a few incoming energy sources will be able to excite the electrons enough to push them to the conduction band all the way. So this is the signature of an insulator. The insulator will be more or less similar to a semiconductor. The only difference is the band gap is much higher. So the concept remains kind of like the same. All right, so this is where we were. Now, one more thing that I want to clarify and mention is that the concept of intrinsic Fermi level. So whenever a semiconductor is in intrinsic condition, so you have, say, conduction band and valence band, where is the Fermi level? Okay, remember the definition of Fermi level is at absolute zero temperature, all the energy states below the Fermi level should be filled with electron, and all the energy states above the Fermi level should be empty, okay, at absolute zero temperature. So apparently in an intrinsic semiconductor, all the states in the valence band are filled, and all the states in the conduction band are empty at zero. Again, I emphasize this, absolute zero temperature. That means there is no thermal energy, absolute zero. KT over Q is the thermal energy, as I told you. If T is zero, you have absolutely zero thermal energy. So no excitation of the electrons from valence to conduction or anywhere else. So then we typically just represent the Fermi level to be somewhere in the middle. If I ask you where to draw the Fermi level, is it here? Is it here? Is it there? I mean, where does it make the most sense? The most meaningful way to show that would be to show it in the middle, right here, as intrinsic Fermi level. This could be the valence band. This could be the conduction band edge. In between, you have this intrinsic Fermi level, showing that, electrons will be completely filling up the states in the valence band, and the states in the conduction band will be completely empty. Right? This is how we typically represent the intrinsic Fermi level. And we will talk about this is intrinsic Fermi level for an intrinsic semiconductor. But when it's no longer intrinsic, we'll see something interesting happening with the Fermi level, and maybe in the next slide or so. In the next lecture. All right, so let's get to the next slide again. Here, we will try to find the position of intrinsic Fermi level. And by the way, I just told you that we just put the Fermi level in the middle. I haven't given you the reason. I mean, we could have put it anywhere within that band gap. Let me use a different color. Maybe I could have put it here. I could have put it here. I could have put it here. Like, what stops me from putting it anywhere else? And why did I choose to put it exactly in the middle? All right. And I'll explain the reason behind it. Let's see. So in here, as you know, in an intrinsic condition, number of electron in the conduction band should be equal to the number of hole in the valence band. So let's start there. Let's put in the equation for N0 and equation for P0, like we saw before. All right, just put that in. And then let's do some math. Try to get rid of the exponent, like basically divide NC with NV, divide the exponent with the other exponent. Like going through some simple math steps, you can arrive at this stage. Just try to solve for EFI. That's all. That's what I'm telling you. Just solve for EFI. Okay, and then you end up with this situation. Now, there is an interesting quantity here. Notice NC and NV, there is a ratio of NC and NV. And if you remember, NC and NV were kind of similar to look at, except for two quantities: the effective mass of electrons, effective mass of holes. Everything else will be kind of the same. So when you take a ratio, everything else will cancel out, and only the effective mass ratio will remain. So you basically arrive here. Okay? So we are trying to connect it to deeper parameters rather than a high-level parameter. Like deeper down, it is basically connected to the effective mass. Okay, there is one more parameter sitting right here, EC plus EV over 2. It basically just mathematically came. So this is EC, this is EV. All right, let me start with something else. Maybe if this is X, this is Y in a scale. What is this point exactly in the middle? Can I say it should be X plus Y over 2? Simple, just geometry. So if this is EC, this is EV, EC plus EV over 2 will be exactly the midpoint between these two levels. Okay, so I'm gonna give it a name. I'm gonna call it mid gap. E, energy at mid gap, exactly in the middle of the gap. Okay, so basically I'm gonna replace this with mid gap energy. Okay, so notice Fermi level minus mid gap energy is a quantity which is related to the ratio of effective mass of electron and hole. Now, assuming that the electrons and holes have the same effective mass, and I'm going to get back to it in a second, but let's assume that they have the same effective mass. I mean, let me ask you for a second, who created the electron? I mean, how was the hole created? Simply because one electron decided to move from valence band to conduction band. It ended up creating an electron in the conduction band, and creating a hole in the valence band. So they were created together, by the way. So ideally, we should consider that they should have the same effective mass. It's like just common sense, right? That should come to our mind first. And assuming that's the case, we could easily cancel them out because they should be the same. And what is ln 1? If I ask you, should be 0, as you know. So if this thing is 0, apparently the right-hand side is gone. So you have E intrinsic Fermi level is mid-gap energy. So the intrinsic Fermi level should be exactly midway between the conduction band and valence band. That's the reason why we do what we do. We basically just draw the Fermi level exactly in the middle, making an assumption that the effective mass for electron and hole would be exactly the same. But remember, that's not true. Okay, for most material, like almost any material will have difference in the electron effective mass and hole effective mass. And more about that later, but for the time being, I'm just going to make you aware of the fact that this is an assumption that Fermi level intrinsically will be in the middle, just to simplify our life. That's all. Okay, now let's move to the next slide. And this is the last slide for this lecture. And after that, I'll stop and take questions. And before I move on to the next lecture, this is a very simple slide to cover. I just want to show you that for different semiconducting materials like silicon, gallium arsenide, germanium, you have specific ratio of effective mass for electrons and holes. Typically, we represent effective mass this way. Mn star equals, say, 1.08 m naught. What does that mean? M0 represents the rest mass of electron. So whenever an electron is free and basically just staying there, you know the value already, 9.11 10 raised to minus 31 kilogram. So that's what 0 is. It's like a universal constant. Okay? But that's not the effective mass of the electron in silicon. When the electron is moving through silicon, it basically exhibits a slightly higher mass than the mass that you know, which is 1.08, like 8% more mass than what you'd ideally expect. So that's the effective mass of electron in silicon. But I mean, instead of representing it as, say, 1.08 m naught, there is a norm to basically just represent it in a normalized fashion, where you just report the number and you just multiply the number with the rest mass later on, because that helps simplify the expression for the effective mass of holes similarly. So imagine in silicon, only in silicon, the effective mass of electron is 8% of the actual rest mass of electron. Okay, let's see how the hole behaves. For the case of hole, effective mass is basically half of the rest mass of electron, almost half, 56%, almost 50%. You see, so electrons and holes don't show the same effective mass essentially. And I can give you the quick reasoning for that. Effective mass comes from the concept of internal force, as I explained in a couple of lectures back. Basically, when a particle is moving through a material, it encounters internal force, repulsion, attraction, scattering, right? And then you cannot accurately calculate those force exactly, but you can measure it indirectly, per se. You can measure the overall effect indirectly rather than individual forces. So that overall effect is lumped together in the concept of effective mass. So turns out when holes flow through the silicon, they don't encounter as much opposition as the electrons. So that's why they appear to be less massive. And electrons appear to be more massive because they face repulsion and scattering by a lot of atoms in a crystal. So that's the reason why the electrons have a higher effective mass and holes have lower effective mass. By the way, that may not be true for all the materials. Interestingly, if you go to gallium arsenide, let's take a look at the numbers. These are basically experimentally measured numbers. See, the effective mass of electron is much, much, much lower, really, really low. But the effective mass of hole is actually quite high, almost as much as in silicon. So what happened here? So for gallium arsenide, electrons can flow relatively freely, almost freely, in a much easier fashion than in silicon. But holes, not as much. So there is a difference. So when you are picking a material for your electronic applications, are you making a device that requires electron flow, or does it require flow of holes? Depending on that, maybe you can make a decision, right? So you have to be aware of the fact that electron effective mass and hole effective mass are almost never identical. And this chart shows you some of these real numbers. And by the way, NC and NV, these are also kind of given. If I ever provide any questions in midterm or final exam, I'll give you the number, so you don't have to worry about memorizing or anything. Finally, one more important thing, intrinsic carrier concentration. These are also experimentally measured. We know the number for silicon, we know the number for gallium arsenide and germanium and other semiconductors as well. Maybe this could help you decide on a few things. Let's see. For silicon, the intrinsic carrier concentration is 10 raised to 10. For germanium, it's much higher. It's 3 orders higher, basically. So intrinsically, germanium is prone to creating more free carriers than silicon. So looks promising, right? Well, just keep that in mind. There might be other challenges, and we'll cover them at some point. Gallium arsenide, on the other hand, they look very promising in terms of the effective mass of electron, which is like much lower, but their intrinsic carrier concentration is really, really low. And we could easily explain that by looking at the band gap of these materials and things like that. So anyways, I will stop with this particular lecture here and see whether you guys have any questions on the chat, or if you want to unmute yourself and ask me questions, please feel free. Are we doing good so far? Are you guys all with me? Anything? No questions so far? Okay, perfect. Thank you. All right, so let's get started. And no problem. All right, sure. So let's get started with the next lecture, which is gonna be number 7, which is the next part of our semiconductor in equilibrium. And remember, we are talking about semiconductors that are only in equilibrium. And I wish I could quiz you on this. What is equilibrium? We are not applying any external voltage, no temperature gradient, no magnetic field, nothing. Basically, the semiconductor is sitting there, and yes, you have a temperature, but remember, no temperature gradient, just temperature. Okay. All right. So you have seen this slide before, the first slide before. We talked about how you can create N-type semiconductors and P-type semiconductors by doping, by introducing controlled impurities and encouraging the material to create extra electron or less than the number of electrons required to satisfy everybody, right? Yeah, so why repeat this slide? So I'm not going to repeat this slide. I'm going to show you how this concept can now be linked with band diagrams. See, we have, when I first saw that slide, we didn't even know what band diagrams are, right? We didn't even know the concept of bands. So now we do. So can we try to merge these two concepts together and see what happens when you have an N-type semiconductor? How does the band diagram look like, or versus P-type semiconductor? And that's exactly what we're gonna talk about now. So just to quickly remind you, when you dope pure silicon or other semiconductors with a material with 5 electrons in the outer shell, pentavalent, you create an extra electron that is not necessary for bonding purposes. So it becomes free for you to share across the structure. So sure, there you go. You create an N-type semiconductor. On the other hand, when you dope it with something that has less than 4 electrons, you create an absence of electron, otherwise known as hole, and the nearby atoms will try to fill up that void, and in doing so create a void in a different location, and then there will be more like a cat and mouse race again, and you create a flow of holes, quite opposite to the flow of electron. Okay, now I'm gonna use 2 names here. The type of material that creates an extra electron is called donor, and the electron that you create is called a donor electron. Obviously, the other type of material which has 1 less electron is called an acceptor. So you have donor type impurity or acceptor type impurity in semiconductors. Just get used to these terms. Now let's see how the band diagram looks like for donor type impurity and acceptor type impurity. Let's start with donor, the N-type semiconductor. So interestingly, let's start from the scratch. Let's see what happens in a pure silicon. You have conduction band, you have valence band. Where is the intrinsic Fermi level? We just talked about intrinsic Fermi level being exactly midway between the conduction and valence band. That's an approximation, but we don't care. Doesn't matter. Okay, just for the simplicity, we assume that it's in the middle. Okay, now when you introduce a donor, where will the donor energy level be? So typically, I mean, if I ask you just based on common sense, without going through complicated maths or stuff like that, would the phosphorus atom that had an extra electron be more open to giving up that electron than the other silicons? The answer should be yes, because what will it do with that electron? It has no purpose. The phosphorus has already created bonds. It has 8 electrons in the outermost shell, so it's very stable in terms of energetics. So it's just gonna ignore the other electrons. Okay, I don't care. Just let it go. So that means in terms of energy band diagram, the donor energy level will be very close to the conduction band. And remember, this is like y-axis. This is like an energy axis. Okay? It doesn't represent any physical location of the donor. Physically, the donors could be anywhere. But energetically, the donor energy will be close to the energy level of the conduction band. What that represents is that it is much easier for you to push these donor electrons to conduction band than creating electron all the way from valence band and send them to conduction band. It's much easier for you to now create electrons. And remember, you don't just dope a semiconductor with one donor, right? We are representing it as if we have just one donor. You have actually billions, even more donor atoms. So you have a lot of electrons piling up in the conduction band coming out of the donors. So, and it's much easier way to create donors. And remember, simply because you have a donor level which can easily create electrons doesn't mean you don't have electrons coming up from the valence band. That process is still ongoing. It doesn't stop, by the way. It just goes as it was doing before in an intrinsic case. But for a doped semiconductor, you now have a surge in electron, which now becomes the major source of electron in the conduction band. That's the only difference here, right? One more thing, when the donor atoms, like here, phosphorus, kind of decides to give up this electron is now free, by the way. So the atom itself, the phosphorus atom itself in there behaves as if it's a positive charge, but it's stuck. It's stuck in bonds with the silicon atoms around it. So it cannot move around, right? It's stuck. But the electron that it just gave up, that electron is a free agent right now. So it can move around the material anywhere it wants, depending on where you are, attracting that electron to, based on the electric field direction. But the point is, when you have a donor level, it can create and supply electrons to the conduction band, and those electrons can move around. They are free electrons, almost free electrons. But this donor levels has positive charges that are stationary. So they're stationary charges. They don't move around. So one thing moves around. When charge moves around, that creates current. Remember, right? When charge is staying somewhere, that's not going to lead to electric current. When the charges move around, only then you have electric current. So these electrons can give rise to an electric current, and donors will stay put. They will not do anything. All right. So whatever I explained, it's also mentioned in detail here in this text. So please read them and let me know if you have any confusion. Now let's get to the other side. Let's talk about the p-type semiconductor. And we already covered this before. So I'm just going to get to the band diagram right away. So for the p-type semiconductor is exactly the opposite. And as I promised, if you understand the n-type case well, it's typically quite easy for you to understand the p-type case because they are often symmetric. So you have, again, your conduction band and valence band. For a p-type semiconductor, you have an energy level that is close to the valence band. And we're going to call it the acceptor level. A stands for acceptor. Okay? It's the acceptor level. Because it's going to accept electrons from the valence band. Now, the valence band can now easily send electrons to this acceptor level when there is some sort of external thermal energy, rather than sending it all the way to conduction band. Sure, it will still send some electrons to conduction band, like it used to do before, but more electrons will basically be sent to the valence band, which is right next door. So now, this acceptor will give rise to, as I discussed in the last lectures, we are not going to talk in terms of electrons anymore because that's a little bit challenging. We're going to talk in terms of holes. I'm not going to say that valence band will give electrons to the acceptor level. I'm going to flip it around. I'm going to say that this acceptor level will provide holes to the valence band. It's funny, but this is how we do things in semiconductor industry. So basically, acceptor will give holes to the valence band. It will create holes to the valence band. That's how we put it. And we describe the holes to be like positively charged particles. So basically, you have positive charges piling up in the valence band, And and what happens when you get an extra electron from the valence band, by the way? You become negative. So these acceptor levels, they will become negative, but remember, they're stationary. Why are they stationary? Because they're stuck in the crystal. They're basically stuck in bonds with other silicon. So they cannot move around. So these charges cannot move around, but the ones that they create in the valence band, they can freely move around and create an electrical current. Okay? So that's the main concept. For both case, N-type or P-type, these doped semiconductors are also mentioned as extrinsic semiconductor, just to maintain some similarity with the term intrinsic, right? So when you don't dope a semiconductor, you have intrinsic semiconductor. When you dope them, they become extrinsic. So both N-type or P-type are extrinsic semiconductors. Okay, now let's see how the Fermi functions and density of state functions look like for an extrinsic semiconductor. We looked at this similar graphs for the intrinsic case before in the previous lecture, but now it's time for us to modify that understanding and see how things change when you dope a semiconductor. Please let me know if you have any questions. At least speak up or maybe just quickly check the chat one more time. Okay, no question as of now. So let's get back to, let's get back to this and talk about what happens when you dope a semiconductor. So this is your conduction band, valence band. I mean, this diagrams look scary, I know, but when you start breaking things down into smaller, constituent, it becomes really manageable and easy to understand, honestly. So this is conduction band, this is valence band, this is the intrinsic Fermi level, and we agreed to put it exactly in the middle, as for the reason I described before. Let's see, when you dope this semiconductor with maybe like a donor, the new Fermi level, this is the Fermi level, not the intrinsic Fermi level. This is the actual Fermi level in the extrinsic situation. When you dope the semiconductor, the Fermi level will go up. And let me explain the reason here. What is the Fermi level? Fermi level shows the level up to where you could find electrons, right? Say, intrinsically, we draw the Fermi level here because there is no donor. So the last level where you could find electrons would be up to the valence band. And then there is nothing, unless you provide some energy and it goes up, right? But for the extrinsic case, this donor, this atom, which is the donor, it already has more energy than the midway, the mid-gap energy, as you see. So apparently our Fermi level cannot be portrayed to be in the middle anymore. The Fermi level will have to be up to this point because that's where electrons are. Electrons are already here. Let me use a different color. We already have electrons here. So why would we show the Fermi level down there? Because no electrons can be above the Fermi level at absolute zero temperature, right? So that's why we have to modify and say the Fermi level is now here. So with doping, all you're doing is changing and modifying the position of Fermi level. Remember that. This is another way to put it. You're basically changing the Fermi level from midway to either up or down. So if I take a empty slide here, take a conduction band, valence band, intrinsic Fermi level. Now, with N-type doping, you take your Fermi level closer to the conduction band. With P-type doping, you take your Fermi level closer to the valence band. As simple as that. Okay, and then when the electrons are here, they can quickly go to the conduction band. On the other hand, when the Fermi level is here, these electrons can go to the upper layer. Electrons will always go up when they get external energy, by the way. So it's not going to be opposite. Electrons are always going to go up. But for the second case, we just flip it over and we portray this in a way that, oh, electrons are not coming. Holes are going to the valence band. This is just, to simplify our life. That's all. That's the only difference for valence band and P-type doping. But apart from that, the concept is quite symmetric. Okay, now, as I told you, we change the Fermi level position by doping. If this was the intrinsic Fermi level, when I dope with N-type dopant, I should assume that the Fermi level will go up, and that's what you see here. This is the Fermi level. Okay, now I want to take a step back here and try to draw the Fermi function. If you remember the Fermi function, let me just draw it this way. F of E, or if, however you want to put it. This is energy in the x-axis, and this is Fermi function in the y-axis. The Fermi function was like this. If you remember the equation properly, okay, this was the Fermi energy, and Fermi function, let me just put it there like this. Exponent E minus EF over KT. It's like that, somewhat like that, okay? Now, and why do I choose this gradual case? Because it's maybe non-zero, not absolute temperature, absolute zero temperature, okay? It's above absolute temperature, some non-zero temperature. So you have something above Fermi level as well. Otherwise, if it were exactly the zero temperature, then you would have a situation like this, like the green one, right? Okay, now notice this transition occurs at Fermi level. The transition occurs at Fermi level. Now, if I ask you, what if I change the Fermi level to this position, say EF2? What should happen? In that case, the transition should occur. Let me choose a color here. The transition should occur at that Fermi level. You know, so by moving the Fermi level somewhere, you are moving the point where the transition occurs. So that's what you will see here in this case. So previously, I mean, if you could compare them side by side, then you would see this was the intrinsic Fermi level. I need a different color. This was the intrinsic Fermi level, and the transition used to occur here, and as the red line suggests. But by moving the Fermi level above, by doping, you have basically shifted the Fermi function. Okay? Doesn't look like it, but you have done that. And I mean, if you could go back to the previous lecture and check the previous slide, you'd see for an intrinsic semiconductor where you didn't have the Fermi level here, you had the Fermi level in the middle, the number of electrons and number of holes were exactly the same. So these were equal. N0 and P0 were the same. But, and again, do you remember how we got N0? N0, we basically integrated the density of state function in the conduction band with Fermi function with respect to energy, right? And we performed the integration from ECE all the way up to infinity. So ECE up to infinity. So there are some maths and whatnot. It doesn't matter. The point is you have now shifted the function. So the product and the integration will change. And if you do the math, you will see you have more area in the conduction band now, and the area represents number of electrons. And as the Fermi function shifts up, you have less overlap here in the valence band, and this area reduces. So you create more electrons in the conduction band and less electron in the valence band. Again, see, people, especially in engineering, they love to use math to express simple things. I mean, I could have explained that verbally. If you dope a material with N-type material, N-type dopant, obviously you'll create more electrons in the conduction band. Then you could have otherwise created in pairs. So in pair, when you were creating electrons in pairs, they were equal in number of holes, number of electrons. Now, if you create more electrons, oh, not this one, I meant to use. If you create more electrons by doping, obviously you end up with more electrons than holes, right? It's common sense, as you see. But mathematically, people love to express things mathematically. That's the reason why you see this type of geometric expression in the textbook, the same integration repeated over again for a new Fermi level, and you can mathematically demonstrate that you get more electrons here in the conduction band and less number of holes in the valence band. Now, quite opposite for p-type. For p-type, you basically move the Fermi level down. Instead of in the middle, you just move it down. And exactly the opposite scenario occurs. The area of this curve increases, the other one reduces. So basically, we could just portray it in a way that you have more holes than electrons. Simple. Okay, so it's all about shifting the Fermi level. And right now, at this stage of the course, we are moving the Fermi level by changing the doping, right? We are doping it using N-type material or P-type material. So N-type dopant or P-type dopant, and that's how we are controlling the Fermi level. But you'll see in a few lectures down the line that there are ways to change the Fermi level by applying external voltages in certain way. And if you could modulate this Fermi level, if there is one takeaway that you should consider from this concept, if you could modify this Fermi level, take it up, this will grow. Or if you could reduce the Fermi level somehow, take it closer to the mid gap, this will reduce. So you could change the number of carriers available in the conduction band by dynamically modulating the Fermi level, which is very powerful, by the way. This concept is powerful because that means all we need to do in engineering would be find ways to modulate the Fermi level. Take it up, take it down, and thereby you could increase the number of electrons, reduce the number of electrons, do whatever you want. That's very powerful. That's what leads to the controllable conductivity in semiconductor. And I told you the reason why we love semiconductors is not because they're not as good, not as bad. I mean, that's not a qualification, honestly. That's a limitation per se, right? The reason why we love semiconductors is because we can modulate their conductivity. We can make it better or worse at will. So this is where it comes from, by modulating the Fermi level, taking it up, bringing it down, or whatever you want to do. And you have two variants, N-type or P-type, at your disposal. And by using both types, you can make some interesting devices. And we will learn that in this course. Now, let's move to the next slide and talk about, obviously, again, some maths. Trust me, if you just pay attention, you probably never have to worry about them again. In engineering, in most textbooks, in most literature, you have to deal with math. So I have to go through some maths. But most important fact is the take home. What is the big picture? What is the message from the math? Okay. So we'll get there in a second. Remember this equation. This literally comes from the previous lecture. We went over, we didn't do the math in every step, but I showed you how that steps are done to calculate the number of electrons in the conduction band. And remember that conduction band energy, Fermi level, NC, we spoke about NC quite a bit, temperature, all of these are old stuff. Now, let's do some simple matrix. And that's what I say here. Just add intrinsic Fermi level in both EF and EC. Basically, just do this. You see, if you do the math, they will cancel each other out. They're not even there. But we just deliberately added them. And then you could consider this section, and as you see marked here in red, this section is nothing but the intrinsic carrier concentration, because you have EFI inside. So this could be replaced as NI. And then you have an extra term for the extrinsic carrier case. For the extrinsic carrier, let me just get to the final equation here. The number of electron will be the number of electron in the intrinsic case times, I mean, it will depend on the difference between the Fermi levels. The actual Fermi level and the intrinsic Fermi level. Notice that? By the way, I forgot to mention one thing here. What changed in the equation? This equation is basically same as before. There is just one change. I mean, I really wish I could have asked and made you respond. But apparently in the previous slide or previous lecture, we used to use I, which was intrinsic, because all the Fermi levels before were all intrinsic. We didn't even care about the extrinsic equation there. But now we will have to mention the actual Fermi level, not the intrinsic, because the material is not intrinsic. It is extrinsic now. So that's the only thing that changed. But we deliberately added intrinsic in the picture in a way that they will cancel each other out. And then we separated out the Fermi levels, two Fermi levels, extrinsic and intrinsic, to see how they interact with each other. Okay. And then we basically just replaced our previous equation for intrinsic carrier concentration here. Now, this is the take-home message. This equation shows you the number of electrons in an extrinsic semiconductor is related to the intrinsic carrier concentration. But it will go up or down depending on the difference in the Fermi levels. So notice one thing. What is EF? I don't want to get to a different slide because we need this equation, but I want to draw something here. This is EC, EV. This is EFI, which is intrinsic Fermi level. And let me draw the other Fermi level, the real Fermi level here, EF. So EF minus EFI basically represents the difference between these two Fermi levels. What it shows you is if this difference increases, the number of electrons increases. Now, if I ask you, how can I increase this difference, EF minus EFI? Well, common sense will tell you just move this EF higher up, and then you have a higher difference between EF and AFI, and that will lead to more electrons. And you can see it the other way. The closer the Fermi level gets to the conduction band, the easier it gets for the electrons to jump over to the conduction band. So yeah, makes sense to have more electrons, right? So you could easily use the math or you use common sense. Either ways, you reach the same conclusion. You might ask me, why do we still need the math if common sense gives us everything? Because common sense tells you what will happen, but it will not tell you how much, right? How many electrons exactly. Is it a billion? Is it a trillion? Is it 1,000? You don't know the exact number. You just know that something will increase or decrease. So that's why you need math. This will help you calculate the exact number. So we need both. We need common sense. We need math as well. So this equation could easily be translated to, as I mentioned, for the holes, and you end up with a similar expression for the holes as well. So I don't want to, as you see, similar calculations. I don't want to go over it all over again. It's also related to the difference between Fermi levels. That's all. All right. One more thing to point out, for intrinsic case, number of electron, number of hole were the same. So we used to call them intrinsic Fermi level. And the Fermi level and intrinsic, basically for intrinsic case, they are the same thing. For extrinsic case, and remember, there is a typo here. I'm just going to point it out. I forgot to delete this part. So obviously, for extrinsic case, there is doping. Otherwise, why is it in extrinsic, right? So for extrinsic case, the Fermi levels are not the same. So number of electrons and number of holes will not be the same. One more take-home message that I really want you to focus on. So in an extrinsic semiconductor, yes, as you dope it, you get more electrons and more holes, obviously. But you also notice that intrinsic carrier concentration, Ni, is already there. So if a semiconductor has more intrinsic carrier to begin with, right? To begin with, you already have more electrons. Then it will be easier for you to create even more electrons. Notice that? So there is a need to choose a material that has a higher intrinsic carrier concentration to make more carriers. But if a material has a really, really low carrier concentration to begin with, no matter what you do with Fermi levels, you can only do so much because this will kill you, right? This intrinsic carrier concentration will diminish the effect of Fermi engineering, Fermi level engineering. So keep that in mind. That's why the very last slide in the previous lecture, where you had a chart showing the Ni, intrinsic carrier concentration for silicon, gallium arsenide, germanium, should be of interest to us because we need to choose which material to use. And silicon has pretty good intrinsic carrier concentration. That is one of the reasons why we chose to go with silicon, not some other material. That's not the only reason. There are other reasons, obviously, but that's one of the reasons. I mean, imagine if silicon had a really bad or low intrinsic carrier concentration, then no matter what you do with silicon, you would never be able to do, proper engineering with them. So just keep that in mind. Okay, let's move to the next slide and see this simple equation is very powerful. And I'll tell you what. Imagine E equals mc squared. I'm sure you've seen more complicated equations than this, right? Any differential equation will look more complicated than E equals mc squared. But you know the implication of this equation, right? Like extraordinary. So similarly, this simple equation that you're looking at here, N0, P0 equals Ni squared. It looks super simple, but it has a very deep implication, and I'm gonna explain that in a second. But let's say how that equation comes into being. That comes from the previous slide. So we calculate the number of electrons in the conduction band and number of holes in the valence band. Let's take these two equations. Let's consider this to be equation 1, this to be equation 2, and let's get to the next slide. Multiply equation 1 with equation 2. Simple, just math. And you end up on the left-hand side with N0, P0. On the right-hand side, you do some math. You merge these two exponents together. You end up with band gap, EG, right? I mean, you'll end up with a situation where you have EC minus EV and you replace that with EG. EC minus EV is basically the band gap. That's what. So you get this equation. But then you immediately remember that in the previous lecture, we talked about the expression for Ni, intrinsic carrier concentration. If you don't remember now, please go back and take a look at the previous set of slides for the previous lecture. And there was a slide about Ni squared equals exactly this quantity. So we realize, oh, okay, that's Ni squared. Just put it in there. And then you arrive at this simple equation, N0 times P0 equals Ni squared. Now, let me explain why it has a deeper meaning. Notice when you somehow increase your uh, electron numbers, concentration of electron, N0, if N0 goes up, the product of N0 and P0 will have to remain the same because their product will always be equals Ni squared. And Ni squared is kind of constant for a material. It's material property. It's coming from silicon or germanium or gallium arsenide. So silicon has a given Ni which will not change. So you cannot go beyond that. All right. So if you increase N0, you have to adjust P0. Obviously, it has to go down somehow to create the same Ni. So if you create more electrons, the total number of holes in the system will have to be adjusted accordingly to maintain the same Ni. Just remember that. Okay. So it doesn't matter how you're creating this electron. Are you creating by doping? Are you creating by, other means? Doesn't matter. If you have more electrons in the system, electrons will dominate the overall property of the material, and they will lead to less and less holes, so that the total product of the total concentration becomes Ni squared. So this is an interesting thing. That's why when you have more electrons in a system, they dominate the property because they basically diminish the number of holes in the other level. They basically, the holes will be known as minority carrier in that case. So that's what the second point tells you. When you have more N0 in a system, electrons are called the majority carrier and holes are the minority carrier, obviously. On the other hand, when you have higher P0 than N0, holes will be the majority carrier and electrons will be the minority carrier. And the majority carriers will determine the type of semiconductor they are. If you have more you might be wondering why is he repeating that? Because remember, in any semiconductor material, you have both electron and hole. That's the thing. If you haven't noticed that yet, you should. In any semiconductor, because electrons and holes will be created simply because of temperature, right? Even if you don't dope them, you dope them in a way that it creates more electron, but there will also be some holes because there will be some thermoelectric effect, thermionic effect. Let me just go back here. That creates electrons and holes simultaneously. So any material will have holes and electrons because of thermal processes. Yes, some will have additional electron or additional hole, but the properties of the material will be mostly governed by the majority carrier. Now, and there is a fundamental limit, as you see. You cannot just get any number of electrons and holes in a system. Like, okay, I want this many electrons, that many holes. No, you cannot have it. They will adjust each other. They will basically, we use the term annihilation because an electron can always pair up with a hole and annihilate each other. So they will basically annihilate each other to keep this equation fixed. So just to satisfy this equation, some electrons will, pair up with holes and they will both be gone. So this is how significant this equation is. All right. Let's move to the next concept, degenerate and non-degenerate semiconductor. And we are going to cover a few other concepts here in this lecture. Let's see how much we can do. We still have 9 minutes. So degenerate and non-degenerate semiconductors. Let's talk about it. So, so far, when we talked about doping, you might remember that slide that I've used quite a lot, this one. We just show the dopant atom to be like an outlier somewhere, like just one of them, right? And there are many silicon and just one dopant. It's as if the dopant has no other neighbors that are also dopant. But that's not true. There are other dopants. You just don't dope with one. There are many other dopants in the system. So as long as you don't use a lot of dopants so much that they're close by and they can interact with each other, you can ignore dopant-dopant interaction. For example, maybe a boron atom interacting with another boron atom. Maybe if the doping concentration is low, then you can essentially ignore their mutual interaction, which is the case, which has been the case so far. We have kind of ignored it. And a situation like this, where the dopant number is so low that the dopant atoms don't interact with each other, essentially, is called a non-degenerate semiconductor. Okay? Basically, we are dealing with non-degenerate semiconductor mostly. So far, we have been doing that. But imagine if you dope a material so heavily, like there are many dopant atoms, that the dopants are kind of close to each other, Let me talk about it again. I'm going back and forth. Sorry about that. So imagine if you have a dopant atom right here as well and here. So they're kind of close to each other. And boron, they're heavily doped material. So in a heavily doped materials, this dopant atoms will also interact with each other. And there is a quantum mechanical significance of this interaction, by the way. Remember in a couple of lectures back, we talked about what happens in a system. In a system, like when two systems interact with each other, a system could be an atom, a crystal, something like that, then the electrons will need to take up quantum tags, and two electrons cannot have the exact same tag, by the way. So when they become part of an interacting systems, you have to provide tags to the electron. And then what happens? Remember that every energy level will split up into multiple. So if two atoms are interacting, you have to split them into two levels. If three atoms are interacting, you have to split them into three levels, and so on, right? So the more atoms interact with each other, the more splitting will occur, and that splitting gives rise to band. So where am I getting with that? Remember in the band diagram, I'm sorry, I'm just looking for a empty white space. Yeah. In the band diagram case, so you have EC and EV, and I drew the donor level to be like, okay, just an energy level, nothing to worry about, right? That's how the situation was. But if the donors themselves start interact, why did we end up with conduction and valence band? Notice the term band. The reason why we ended up with a band in silicon was because the energy levels split up. Not here. The energy levels split up. I meant to draw it like this, EC and AV. Energy levels split up in the valence band and in the conduction band. So they basically split up. That's why we had bands, not just levels, we had bands. So now similarly, imagine if you have a donor level sitting in here, which doesn't interact with anybody else. Sure, this is good enough. But when they start interacting with each other, all on a sudden, you create a level. Instead of just one energy, you create a range of energy. So now you have its own band. This thing becomes its own band. So you have a donor band then. Now, what is the significance of that? The significance is you can no longer say that the Fermi level is at the donor level. You cannot just say that anymore, because the Fermi level will be higher up, because the electrons can be all the way up to here as well. Does that make sense? I mean, I hope it does. If not, please ask me questions. So what I'm trying to get to is, then you can no longer portray that let me use a different color. You can no longer portray that the donor level or the Fermi level is here. The Fermi level will actually go up in the conduction band, inside the conduction band. So practically, this is the donor level. This is the donor band. Instead of a donor level, we have to say donor band. And the top of the band will represent the Fermi level. And the Fermi level will now be inside the conduction band. So that's called a degenerate semiconductor. Essentially, if you heavily dope a semiconductor, the donor levels start interacting with each other and they create their own band. And the band then pushes the Fermi level inside the conduction band. And here is why that is fascinating and useful. Imagine, let me just get to this empty page again and draw two cases for you to better understand. We have a few minutes. Hopefully, we'll be able to complete that very comfortably. So this is conduction band. This is valence band. This is conduction band. This is valence band. I'm going to show you two cases. Imagine you have Fermi level here. You have some electrons, and the electrons can go up to the conduction band with some small amount of energy. But what if the Fermi level is right here in the conduction band? So whatever electron you have in the Fermi level, they are already above the conduction band. So they are already free. They're basically born free. The other electrons will kind of free. They can get some energy and become free. But between A and B is much better conductor because they always have free electrons. They don't need any external energy at all. They're always going to be free electrons available. So this is a much better conductor. Okay. Now, for this material, which is N-type essentially, we basically just use the notation N-type silicon. For the other kind, the degenerate kind, we have to distinguish between them. We use the term N plus silicon. That's how the degenerate semiconductors are noticed. Now imagine if you keep doping it again and again, like basically you keep increasing the doping concentration. What happens to the Fermi level then? The Fermi level keeps going up. So we keep using more pluses. Like instead of N plus, we could use plus plus just to represent that it's even more heavily doped. Okay. So typically in a device structure, when you have different type of doping concentration in different zone, we could use N type here. Maybe the other one is heavily doped, more heavily than the one on the left. So you could use N plus. If the next one is even more heavily doped, we could use N plus plus and so on. Right. Now that you know the type of notations we use for degenerate semiconductors and non-degenerate semiconductors, I hope when you see a device diagram in future, it will be easy for you to identify, oh, okay, you are heavily doping that region. There is a reason, okay? So just to give you a realistic example, the MOSFET device that we talked about and we'll read about it, it has source and drain and gate terminal. Source and drain terminals are N plus because they are heavily doped. You'll see that soon and you understand the reason why they are heavily doped. But the other region, this region, is not so heavily doped. So we just use P. We don't use P plus there. Remember that. Anyways, so now you understand what is degenerate, non-degenerate. Oh, by the way, whatever you do for N, just revert it for P. So for P-type non-degeneracy, imagine you have conduction band and valence band. For P-type degenerate semiconductor, the Fermi level will go inside the valence band. For N-type, Fermi level goes inside the conduction band. For P-type, it will go inside valence band. Just the opposite. Simple, like I promised. If you understand one of them better, the other one will be just almost like a flipped version of what you just understood. All right. So, and charge neutrality, I already covered this, and even before we started discussing this, no matter whether it's an N-type semiconductor or P-type semiconductor, they are not positive or negatively charged. They're essentially charge neutral because that extra electron that the phosphorus gave up, it's basically in terms of the overall structure, the phosphorus become positive, but the electron is still there. It's not getting out anywhere. Okay. So the overall material is still charge neutral. Similarly, for P-type semiconductor, it's not taking an electron from an external source. It's basically staying within the crystal itself. So essentially, this N-type or P-type semiconductor are both electrically neutral. They are not positive or negative. Okay, just keep that in mind. Now, I don't want to get started with compensated semiconductor. This could be a really nice way to begin our next lecture, which will be in person in Knoxville. So, I'm eager to see you guys back in class again next Tuesday. Let's stop here today. Thank you so much for your help and flexibility and, cooperation. Take care, everybody.